Okay, very good. We got the recording going. All right, class announcements and important information that you folks probably want to know. I'll remind you to always go over here and click on the calendar. Well, not the inbox, the calendar. Let's try that again. Go over here and click on the calendar. And so that's loading. It's thinking about it. There we go. And I have a number of classes going, but our class is here in blue. And so the only thing we have due this week is there is a discussion page that a lot of folks have done on basic electrical measurements. And there's also the SP2 safety test. And again, I was just going through and giving people points for completing their activities. Looks like a lot of you folks have already done that. Which is absolutely fantastic. So periodically in class, go through there and look at the calendar to see what's coming up. Next week, our big activity for this class will be for you to get yourself a multimeter. And that could be like one of these cheapy ones from Harbor Freight. It could be a professional quality one, like the Snap-on here. It could be, or anything in between there, that would work, but we want it to be a digital meter. Now that being said, I have been working with my tool room techs to try to put out kits. And what I wanted to do, and we can do this on the chat, is I wanted to see if any folks would like me to put together the kits, or does most everybody in the class already have a meter that they want to use? Because what I can do is have the tool room guys round up some meters. In fact, we're in the process of working on that right now, and put them in plastic containers and send them out your way, like set up a time for you guys to come by the college and stop by the ranch house or something and pick those up. We're doing that for some of the classes in electronics. Even horticulture is doing something where students can drive by and pick up seeds and stuff. So the college is doing some of those activities. So let me know on the chat, and you can chat it to everybody, or you can send even me a private message on the chat that says, yeah, I could use a meter, and that way I can plan accordingly and get these things put together. All right, so I did the need a meter announcement. The other thing I want to do, we're kind of related to tools and things, is that next week, actually, in my other class, that class meets on Tuesdays, but on that class, we're going to have a guest presenter from Matco Tools, Rick Best. Now, some of you guys that have been with us for a while, you've probably already heard from Rick, and you know that you can get 50% off of Matco Tools and Snap-on tools for that matter. But those of you who are new, you might want to come to this on Tuesday. So that'll be Tuesday night at 6:30 next week. You're more than invited. I'll put an announcement up on our class announcements, so you can check that out. But I'd love to have you here. If you've never heard the spiel, so to speak, never heard how you guys can get tool discounts, you really should take the time to do it. Because if you're a tool hound like myself, or you are planning to enter the automotive industry, you're gonna at some point need to have your own tools, and it's the cheapest way you're gonna be able to buy professional quality tools. All right, so that's next Tuesday. What we're gonna get into tonight, though, is finishing up our electrical presentation that we started last week. So we started this basic electricity presentation right here. I'm going to change my screen share because I've already loaded that thing up. I'm going to change my screen share so we can look at it. I think. Let's see. Let's try that again. Okay. There we go. And let's see how we can go through this guy right here. Last week, where we ended up with this is on this particular slide right here. And let's see if I can make that a little bigger for you. All right. And so we talked about voltage, current, and resistance. And remember that one of my pet peeves here is that there's no juice, right? It's voltage, current, and resistance. And so voltage is like your water pressure, it's your electrical pressure. Let me change that color so we can actually see it a little bit better. That's like your electrical pressure or your water pressure. Current is like your water flowing through the hoses or through the pipes. And resistance is a kink in the hose. Now, current is actually what does the work. In fact, I'm going to type that down because that's super important to understand. Current so if we think, well, what's actually doing work in an electrical circuit? What's making a light bulb turn on and glow? That's the current. What makes an electric motor spin? The current flowing through those windings making magnetic fields makes the motor spin, okay? So current does the work. However, I'm not going to get any flow, any current, if I don't have any pressure, right? So I need voltage to have current flow. Well, what about resistance? Well, I don't necessarily want a lot of resistance, but resistance is kind of nature of the beast, right? Whenever I have current flowing through wires, I am going to have some resistance in those wires. And actually, in a circuit, we do engineer resistance into whatever component we want to operate. So for instance, again, if I have current and I'm trying to get it to, let's say I want it to flow through this wire, and then it's going to go through a light bulb filament here. And let me get my annotations moved out of the way. So let's say I'm going to have this current and it's going to flow through. It is it's going to flow through that light bulb that looks really bad. And when it flows through that light bulb, of course, we expect the light bulb to turn on and to glow there, right? Well, it's actually the electrons flowing through this light bulb, right? It's these electrons flowing through there that do the work, and actually, as they ram through that little tiny filament inside the light bulb, they cause it to glow. So current does the work, as we talked about a minute ago. Well, where is the resistance? This filament inside the light bulb actually has a fixed amount of resistance. I shouldn't say fixed, it has a certain amount of resistance. Why is it not fixed? Because actually as the light bulb heats up, its resistance increases. But where's the resistance supposed to be in the circuit? At the light bulb. So what I mean by that is that the wire here leading up to the light bulb, this wire right here, I really don't want to have any resistance there. And I really don't want to have any resistance on that side either. Where do I want the resistance to be? I want the resistance to be around the component I'm trying to operate. So What is resistance? It's opposition to flow, and you can relate it in a water circuit to a kink in the hose. If you are engineering an electrical circuit, where do you expect your resistance to be? I want my resistance to be at my appliance, the device I'm trying to operate, whether that's a light bulb, an electric motor, a fuel injector, an evap canister solenoid, whatever electrical device I want to function, that is my appliance. That's where the resistance should be. Resistance will be present at other parts of the circuit, but we want those other parts of the circuit to have relatively very little resistance overall. Okay, so voltage, current, and resistance, these guys all work together in a relationship, and that relationship is called Ohm's law, because George Simon Ohm, a couple hundred years ago, just about now, figured out how these three guys work together. So what does that relationship say? Well, if you wrote a paragraph about it, it would say exactly this, that the current flow going through the circuit is proportional to how much voltage you have applied to the circuit and inversely proportional to the resistance. And it becomes pretty wordy, right? Current flow directly proportional to the voltage applied, inversely proportional to the resistance impressed upon the circuit. What are we trying to say? Well, the current flow, that is going to be related to how much voltage I have and how much resistance I have. And mathematically, I can calculate that out. Now, this looks kind of weird. We have E equals E over R, or E over IR in this Ohm's law pie chart right here. E stands for electromotive force or voltage. I is kind of an old term for current. It comes from French, and they would call it intensity, if you will. That's the current flow, okay? So another way to say this would be, I'm gonna replace the E with a V here for volts. And I'm gonna replace that I with an A for amps, and then I'll replace the R with that Greek omega symbol, like we would see on our multimeter to measure ohms of resistance. So the current flow, the amps, it's going to actually equal the volts divided by, the ohms. It's a pretty bad omega symbol. So the amps equal the volts divided by the ohms. What I like about this little pie chart here is I can mathematically manipulate this equation all around. That's just basic algebra. So because I can, let's see, I'm getting a little bit of feedback here. Hey, Susan. Because I can mathematically manipulate this around, all I have to do is cover up what I don't want with my fingers. So I'm going to try my best. I'm going to draw a big finger here, and let's say I don't know what the resistance is, I don't know what the resistance is. So if I cover that up with my finger, that's what this orange thing's supposed to be, my finger. That tells me, oh, that's the volts divided by the amps is going to equal the ohms. Okay. Well, what if I covered up the volts with my finger? Well, so I got to erase that one. That would tell me that, oh, the amps multiplied by the ohms equals the volts. So I can basically manipulate that all around. Now, in an electronics class, and I think I shared with you guys last week, man, I had to do this for hours and hours and hours. I would have one Ohm's law math page to do for homework after another. And a lot of electrical classes and electronics classes, you do these equations a lot. Why do we do the math? The math is an easy way to prove the relationship. So I don't care as much about you guys doing the math. What I care about is that you understand the relationship. So in our cars, we usually have a fixed amount of voltage from our battery, right? Most vehicles that you're going to be working on, unless you get on hybrids and stuff, and they still have auxiliary batteries that are 12-volt batteries as well, but most vehicles are going to have a 12-volt battery on them, a fixed amount of voltage. Now, we know that that 12-volt battery really should have 12.6 volts on it when it's fully charged. And if the car is running, you're going to see maybe 13.8 to 14.8 volts. Some cars might be as high as 15.2 with their charging systems. But somewhere between, let's say, 12 and 15 volts, that's how much voltage I have on tap to run my electrical devices, right? So I have a fixed amount of voltage. So with that fixed amount of voltage, with that 12 volts, if the resistance goes up, that means that Ohm's law is telling us, hey, the current flow is going to go down. Likewise, if I drew this the other way, if resistance went down, then the current flow would go up, okay? So what's really important to understand with Ohm's law is just the relationship of how things work. I've had students and technicians tell me, oh, I worked in the field 30 years. I've never done the Ohm's law a day I worked in the field. And my argument to that is, if you've ever done electrical diagnosis and maybe you spotted things like this, really you were doing Ohm's law, you probably didn't realize you were doing Ohm's law. So in this picture I have, it says a soon to be no start condition due to corrosion, right? Electrically, what's happening here? Well, this corrosion that we see right here, it's going to lead to increased resistance. So the ohms are going to go up due to this bad connection. Okay. What that means is, because we know that, hey, this is a 12-volt battery, right? It's not going to have 50 volts in it. It's got 12. That's what it's, at best case scenario, that's what it has when I go to start my car. So if this connection causes an increase in resistance, Ohm's law says, hey man, that means that the current flow, the amps, it's going to go down. Now remember, what did I say does the work in the circuit? Amps does the work, right? The current does the work in the circuit. So because of that, if the resistance goes up, the available amount of current flow goes down, and that means that our car's likely not going to start. It might just go click, 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 and not crank over, or it might not do anything at all. I'll never forget it. Very early in my career, and I was taking classes at the college, just like you guys are, and my best friend in school called me after work, and he goes, man, I've been working on my grandfather's car all weekend. It won't start. It won't do anything. I think it's got a bad connection or bad ignition switch. I need you to look at it. And I was finishing up work. I was dead tired, but I said, I'll go look at it. Well, I went to look at that car. He had the whole dash ripped apart. I mean, just like everything electrical that you could take off the car seemed like was taken off the car. And when I first looked at it, it was kind of overwhelming how much stuff was apart and wires all over the place. And, I took a deep breath and I said, okay, let's keep it simple. Let's get back to the basics. And so some of you guys have probably heard of the KISS formula, right? Now, KISS, it stands for keep it simple, okay? And my my mentors that taught the KISS formula to me, they said that KISS stood for keep it simple, stupid. Now, probably a nicer way would be, I had a young lady in my class and she said, oh no, it means keep it simple and sweet. That works as well, but they always said, hey man, hey stupid, keep it simple. Well, keeping it simple, what's simple stuff to check? I'm looking for bad connections. So, I went to the dash, I did do a couple of measurements, and you're right, there wasn't any voltage at the ignition switch. And I said, well, let me go back to the battery and look at it. It did not look like this, but I wiggled the connections and they were a little bit loose. I took this apart, cleaned it up, put it back on. Now I had power at the ignition switch, and now I had lights coming on in my dash. And so then after we hooked up the starter and a half dozen other things, guess what? That car started up. His problem was right here at the battery. And he had ripped the whole other car apart, because when he looked at this, it didn't obviously look really bad like this. But it was bad enough where it had enough increase of resistance that you couldn't get the current flow that you needed, okay? So the relationship with Ohm's law, if resistance goes up, current flow is gonna go down. Likewise, if the resistance goes down, the current flow is gonna go up. That also happens, and that's what a short circuit is all about. So my argument is, as a technician, if you're doing electrical diagnostics, you'll be doing Ohm's law all the time. However, you might not be realizing that that's what you're doing. So Ohm's law simplified and spelled out, right? Mathematically, if I multiplied the amps times the ohms, I could calculate what the volts would be, okay? If the resistance is low, the current flow is gonna be high. Think of that, that's a short. I'll type it out. That's a short circuit. CKT is the quick way to say circuit, even though I know technically that's not spelled correctly. If resistance is high, current flow is going to be low. So there's a high resistance problem. So resistance is high, current flow is low. Now, if the voltage goes down, the current flow is going to go down. And that makes sense, right? If your battery, and this is a mini little 12-volt battery for one of my carts, if the battery goes dead, right, its voltage drops, obviously current flow is going to go down. So that's kind of self-explanatory. So that's what Ohm's law means. That's the relationship. And I like to think, here's this Ohm's law pie chart, but I can make this like on a slide or a teeter-totter. So if the ohms go up, the amps get smaller, right? Likewise, if the ohms go down, that means the amps are going to get bigger. So that's how that stuff works. And that is why you will need to know and do Ohm's law as you're working on stuff. So here's a basic electrical circuit. In this case, our appliance, or another name for the appliance is the load, is shown as an electric motor. So we're going to have conductors that allow the electricity to flow through them, hopefully with a minimal amount of resistance. What's not drawn on this circuit that I'm going to add to it is, it's probably going to have a control, maybe a safety device. So if I draw that in, my safety device is going to be a fuse. Here's the electrical schematic for a fuse. And here is a switch that can open and close the circuit. I'm going to close it. When I close it, then current flow should flow through the circuit, flow through the motor. It'll make a magnetic field. That should cause the motor to spin. It flows through ground and back to the negative side of the battery. So these three lines here, that's a symbol for ground. And what we do on our vehicles is to lessen the amount of wires that we got to route all around all over the vehicle, because steel transmits electricity very well. It's a pretty good conductor. We can save half the wiring weight. We can cut off half the wires and just use the chassis, in a lot of cases the body as well, of the car to transmit that electricity back to the negative side of the battery. So with electricity, remember, we have to have a complete path for current to flow. So we're going to flow out here from the positive battery terminal through the motor, through ground, and back to the battery. Now, does anybody see anything wrong with that? Anything wrong with what I just said there? You could do, there's a way to raise your hand, or you could put it in the chat. Oops, I'm drawing on the screen and I don't mean to. Well, last week I talked about how really electricity goes by the electron flow method, and that we have an excess amount of electrons on the negative side of the battery, and they actually flow from negative over here to positive. And so there is what they call conventional current flow theory, and that's where we go positive to negative. And that's how it was thought, how it worked. And then later on, when we got the technology and the ability to actually see down to the atomic level with microscopes and things, they realized, uh-oh, nope, that's not how it works. And so the electron flow theory is that, hey, current actually flows from negative to positive. So if you were going to be building microchips and doing electronics, you would really need to think in terms of electron flow, okay? However, if you're going to be an automotive tech, 99% of the time, you can think about your electrical circuits and conventional current flow theory, and you're not going to have any problems with that. Because it always has to have a complete path. So don't get kind of stuck on which way is it going. It just has to have a complete path to go. All right, so in this circuit that we have on the screen, we have our power supply. In this case, it's a battery. Our load. What's our load? Our load is our appliance, or the device we're trying to operate, in this case, an electric motor. Conductors are the wires that allow us to flow electricity through them to get to the load, to get to that appliance. And I've drawn in a protection device, that's a fuse, and a control device, there's our switch. So those are some of the basic things that you would need for a complete electrical circuit. All right. So if I were going to look at a little bit more, a little bit better drawing of that, here's one where they're showing kind of a glass fuse and an actual switch in the ground and stuff. But really, you usually get more of electrical schematics or wiring diagrams. And I like to say that your wiring diagram, well, that is your roadmap to your electrical system. Just like, you know, if you're new to an area and you don't know where the roads go, right? How do you figure out where you're going? Well, you look at a map. Well, these days we probably have our cell phone tell us where to go, but you know, back in the day, you used a map to figure out where you wanted to go. So that's how we're going to be able to figure out what's going on in our vehicles. The average car has 5 miles of wiring on it. If you took all the wires out and you clipped those wires end to end and you just kept clipping them together, clipping them together, clipping them together, when you did that, you'd have 5 miles of wire all balled up in that vehicle. So that's a lot of miles of wiring. And so our electrical diagram or wiring diagram tells us, you know, where's this stuff going? And oftentimes the first step in your diagnosis is to look at that wiring diagram to figure out what's going on. And if you understand how electricity works, you can look at the diagram and not only will you know where the wiring goes, how stuff's wired, but you'll also be able to figure out how does the circuit work. If I clear my drawings here so I can advance the slide, this would be a wiring diagram representation showing the schematic symbols of the circuit we just looked at. So here we have our battery. What's inside a battery? A series of positive and negative plates. So that's how they draw it in a schematic, with a series of positive and negative plates. Here is our fuse, our switch. In this case, we have a light. That's our load or our appliance. We got the symbols here for ground, right? We go through ground, and that's how it gets back to the negative side of the battery. So why do they draw stuff weird? Why do they use these schematics, these symbols? Well, the reason they do is it's just a little bit cleaner and easier for them to draw. And when you have a very sophisticated schematic, there's wires and components all over the place. It would get very busy, and it actually would become harder to read if you try to draw everything out like you see here. So to make the page cleaner and actually make it easier to read, they draw it like this. But you do need some help decoding this information. And so any good wiring diagram should have what they call a key page. So here is our key page. And it basically is like your secret decoder ring, if you will. It tells you what the schematic symbols mean. So that squiggly line, that's a resistor. Here we have a diode. This line, well, that's a wire, right? That's a conductor. And if it's got a number 16, that actually tells us the gauge of that wire. So if it was a line and it had a 12, then that would be a 12 gauge wire. Or if it had a number 22, it would be a 22 gauge wire. Here's the symbol for our alternator. Here would be an electric motor, light bulbs, fuses. They're a little different on this one. Battery. And so you can see that there's a lot of things that are going to be the same. It doesn't matter if I'm looking at a wiring diagram on a Toyota, a Volkswagen, or a Chevrolet. Some things will be the same, like resistors, diodes, batteries, but some things might vary a little bit. So like light bulb, you know, so the key page, if you dig around in your wiring diagram book or at the front of the wiring diagrams, or sometimes it's at the back, but somewhere there should be this page to help you decode what these symbols mean, okay? I got solid state circuitry there. There's some electronics there is what that means. These wires are crossing, but they're not connected. These ones are connected. So this is a great example of a key page to help you decode what are the symbols in the wiring diagram. Once you understand what the symbols are and you can follow the lines or the wires around, well then you're well on your way to reading that roadmap and figuring out where stuff goes. And then if you think about how electricity works with our Ohm's law, then you can start to figure out how the circuit works. So reading wiring diagrams, yeah, it's a big deal. And as you start to do it, it gets easier and easier and easier. Find the key page, and that will help get you going. All right, so now that we've looked at an electrical circuit and some examples, we've talked about wiring diagrams, we need to talk about the types of electrical circuits. So the first is the simplest here. It's a series circuit, and with the series circuit, there is only one path for current to flow. So here I have a circuit, I have a 12-volt battery, I got a resistor, and I have ground. There's only one path for the current to flow. That's how it's going to flow. Pretty simple. But here I have a series circuit. Again, one path for current to flow, but now I have two resistors and they're in series. And maybe I have three resistors in series. I could replace those resistors and say, hey, they're light bulbs. I have two light bulbs in series or three in series. So there are some rules when it comes to dealing with series circuits. And that is the amperage is the same, the current flow is the same through the whole circuit, which might seem kind of weird, okay? Because let's say this resistor has 1 ohm of resistance, and this resistor has 11 ohms of resistance. You might think, oh, well, there must be more current going through this guy than there is through this guy. But remember, there's only one path for current to flow. So however many amps are leaving the positive terminal of the battery, there has to be exactly the same number of amps coming back into the negative battery terminal, because there's only one path for current to flow. Now, in my example, if I wanted to figure out how many amps did I have flowing, I could do Ohm's law. I got 12 volts. If I divide that by 1 plus 11, 12 ohms, well, that's going to equal 1 amp. So I have 1 amp flowing out of the battery. That means I got 1 amp flowing into the battery on the other side. Okay? Now, I just snuck in another one of these rules on you. Total circuit resistance, it is the sum of the individual resistances. So all I got to do is add these up. So I added the 1 plus the 11 here. That's how I knew, hey, I have 12 ohms total, and I could then use Ohm's law to figure that out. So the total circuit resistance is the sum of the resistances. And this is as simple as circuits get. A great example of a series circuit is really old Christmas lights. Really old Christmas lights were a big, huge series circuit where you had the wire, you had a light, you had another light, you had another light, you had another light going through there. And if one of these lights burned out, the whole strand would go dark because there no longer was a complete path for current to flow. Now, Christmas lights are no longer made in this format, by the way, but that's how the old Christmas lights worked, and it would drive you nuts because if one bulb failed, well, then you had to go through and look at all the bulbs. That's a series circuit. You might think, well, that seems like a pretty bad design. Why would I use that in an automotive application? Well, there are cases. Sometimes your different sensor circuits are series circuits. Oftentimes your control is a series circuit. So let me give you an example. I am going to erase my little guy right there, and I'm going to redraw this thing with the little lights. So here is my battery. I'm not drawing enough plates on there, but you get the idea. So here's my 12-volt battery, and I got a little light, a little light, a little light. And you know what these lights are? These are the lights on my dashboard to make my gauges light up so I can see my fuel level gauge and my radio and all those lights on my dashboard, right? Well, I usually will have one control for these lights, and that control is in series. So even if I have some lights here that are in series and I got a couple of branches that maybe are in parallel, which we're going to get to in a minute, the control for that is going to be in series so that with one switch, I can turn all my lights on, or I can control the illumination level of all the lights together. So oftentimes your controls for your circuits and your protection devices like fuses are in series with the rest of the circuit that may be wired up differently. So let me clear all that stuff there. And we do need to grab a couple other rules to a series circuit here. And so those other rules are definitely important. And that's this. There's going to be a voltage drop across each point of resistance. What that means is that each resistance takes a little bit of its share of the voltage. And these voltage drops have to equal source voltage. Let me explain what I mean here. We'll look at this circuit right here because it's got the two resistors, okay? Let's say this guy had one resistor and it had 6 ohms, and this other resistor had 6 ohms, okay? As current flowed through this guy, okay, what would happen is I only have 12 volts available. What that means is I have to drop that voltage, or essentially use it up through the circuit, because by the time I get to the other side of the battery, that the voltage is all used up at that point, right? I can't end up with extra voltage there. I only have 12 volts available. I have to use that all up. So what would happen here is that I would drop 6 volts across this guy, and I drop another 6 volts across that guy. And if I added those two together, yeah, it would equal 12 volts. I can't have anything left over. So if I have more resistors in the circuit, if I added another one here, well, it's going to drop some voltage as well. And that means these guys can't both get 6 volts. Maybe they're going to get 3, 3, and now this guy over here is going to get 3. So the sum of the voltage drops have to equal source voltage, and each resistance point is going to create its own voltage drop. I've told you before, I told you last week that the voltage measurement is the most common electrical measurement you'll do. You'll be sitting here with your meter on volts more than anything else. Usually what you're measuring is not just source voltage, but oftentimes you're measuring voltage drop. Because where does voltage drop? Voltage drops across each point of resistance. So wherever I have resistance, I'm going to have a voltage drop. So another way to look at it is voltage drop, or VD, that equals resistance, or ohms. So I'm actually, if I have my meter set to volts and I decide to measure a voltage drop, I'm actually kind of inversely looking at the resistance in that spot of the circuit by measuring how much voltage or electrical pressure was lost at that point. All right. So the total voltage drop has to equal the source voltage, okay? The higher the resistance of whatever particular component or connection, the higher the resistance, the higher the voltage drop is going to be dropped at that point, okay? All right. So just like there was the Ohms guy, George Simon Ohm, there was also this Kirchoff guy messing around with electricity and voltages in the early days of electrical experimentation, right? These were mathematicians and engineers. Later on, you had folks such as Nikola Tesla, and of course, you had Thomas Edison figuring things out. Well, Kirchoff, he came up with a couple of laws based on his measurements and calculations. And his law said, hey, the sum of the voltage drops across all the resistance must equal source voltage, which is what I've been telling you over and over. And he's also saying the sum of the currents flowing into any one point in a circuit has to equal what's flowing out. So remember earlier I said, however many amps are flowing out of the battery have to be flowing back into the battery. That's his current law. Now, he has a third one. The sum of the branch currents has to equal the current flow in a parallel circuit, and that brings us to our next type of circuit. So I'm not going to kill you with all those calculations on this one. What I'm going to do is pause on those calculations for now, and I'm going to open up a different presentation. This is the week 2 presentation. And I'm going to say new share. All right. And this new share, this presentation, this week 2 one, talks about parallel circuits. So with a parallel circuit, now we got a lot more stuff going on because each, just a little bit bigger there. So each path has its own connection to source voltage and its own connection to ground here, right? So there's more than one path now for current to flow. I can have some amps flowing through this way. I can have some amps flowing through that way. And what that means is that each device receives full source voltage. So the voltage drop of resistor 1 is going to be 12 volts. The voltage drop of this resistor 2 is also going to be 12 volts. So that sets up kind of a weird phenomenon, if you will. And that unusual event that occurs, if I can clear my drawings there, is this, that the total circuit resistance is less than the lowest resistive branch, is what that's supposed to say. Total circuit resistance is less than the lowest resistive branch. What do I mean? Well, let me write in a couple examples. Let's say the resistance value of this resistor 1 is, let's say this is 12 ohms. And let's say this one is 6 ohms. Well, what's the total resistance? What would the resistance be if I took my multimeter and I measured the resistance from one end of the circuit to the other with my meter, and I'll draw that meter in here. Here he is. So if I measured the resistance from there to over there, well, guess what? It's going to be less than 12. It's also going to be less than 6. Why is that? Well, if the electrons only flowed from one side, yeah, it'd be 6 ohms. But guess what? Some Electrons are also flowing through that way, right? So that means the total resistance of these guys in parallel is going to be less than the lowest branch. It's going to be something less than 6 ohms. And so that's what this is saying. Total circuit resistance is less than the smallest resistance of the smallest branch. So with that, parallel circuit rules. If a circuit has 2 resistors that have the same value, the total resistance will be half of the value of one of those resistors. So for instance, if I go back to this one, let's say both of these guys have 6 ohms. That's 6 ohms, that's 6 ohms. Guess what? The total resistance of this thing, it's going to be 3 ohms. Okay, because some of it can go through that way, some of it can go through that way. It's like it just cuts it in half. So there's all these great kind of rules for a parallel circuit. And the best thing about a parallel circuit is that if I have these 2 lights and they're both glowing, and one of them has a failure, well, the other one will keep working. So the vast majority of the circuits on our vehicle are actually wired up in a parallel configuration, or they may be series parallel. And I'm going to advance a few slides and we'll get back to those at a later date. But I do like to say, hey, there's only 2 types of flavors here. This is for circuit problems, but really there's only 2 types of circuits, 2 flavors, if you will, and then there's a combination of the 2, and that's series parallel. So you have series circuits, you have parallel circuits, and then, hey, we'll put them together, series parallel. And we do that all over in the case of our vehicle. So I used this example before where I said you might have a knob on your dash and it can change the illumination of all these dash lights. I'm going to make this a light bulb here, go into ground, and I'll make it glowing. I'm going to say that's a light bulb now, and that's a light bulb now. I can change how bright all my dash lights are or make them dim because my control, my dimmer switch is in series and all the light bulbs behind are in parallel. So if one of the light bulbs fails, hey, the other ones keep working. But if my dimmer switch fails, now everything else goes down because that part's in series. So there's series circuits, there's parallel circuits, and then there's a combination of the 2. All right. So every class, one of the things I like to do is give you guys some tech tips. So what I'm going to do is I'm going to try to get a new screen share going. There we go. Okay. And on the screen share, what we're going to do is not just look at the race car, but we are going to look at some of these other images I've brought in. Now, remember earlier in our presentation, I showed you the picture from this guy here, and I showed you this picture of a corroded battery terminal. And I said, hey, if resistance is high, current flow is going to be low, right? When current flows through a resistance, oftentimes that creates heat, and heat can do some stuff. Now you think, well, why would current flowing through a resistance create heat? Well, it's all those electrons trying to ram through that kink in the hose, so to speak, with that resistance. It creates heat. And a good example of that is one of these electric heaters, right? Everybody's seen these heaters before. You plug them to the wall, they do get pretty hot. They do use quite a bit of electricity. They'll noticeably make your electric bill higher. But our rear window defogger in our vehicle, this is how this works. If We basically have a piece of resistance wire, and as we flow the electricity through the wire, it gets hot and releases heat. Well, what that tells you is oftentimes where you have resistance in a vehicle, you're going to get some heat. So how many of you guys have seen a situation where you have a wire that looks like this, where it's all melted up? Here, this had like an inline fuse, and it's all melted down here, right? Now, a couple things could be the cause of this. One, it could have had a bad connection at this fuse holder. And as electricity over time flowed through there, it created heat and it slowly melted this thing down. The other thing that could have happened is there could have just been way too many amps flowing through there, and then the little resistance that this guy had became a big deal. And then that, as electricity flowed through the little resistance that was there, it got hotter and hotter until it melted this thing down. But the key is that where electricity flows through some resistance, over time, that tends to create heat. So if you ever see something melted like that, well, that should clue you up for a couple of things, and that there probably was some resistance there, and also that resistance is going to play into what was going on with the current flow through the circuit. So if I clear this out, you can see there's an arrow pointing to that spot of that fuse panel, right? And it's melted. Again, if there was a bad connection at that fuse, that would be a little resistance. And as current flowed through it, it would get hot and it would cause it to fail. Now, it gets down to a chicken and the egg type of scenario, right? The old proverb of what came first, the chicken or the egg? So here, what came first was the resistance here first, and that caused this, that led to it getting hot and it melted? Or was it that, as Ohm's law says, it was the resistance initially very low? That meant the current flow went up, and as the current flow went up higher and higher, the little bit of resistance that was present at that fuse assembly got hot, and that's what caused it to melt down. You don't really know without doing electrical measurements with your meter, and we'll get into that. But what I do want you to walk away from tonight is that one of my best electrical diagnostic tools, I said it down here somewhere, there it is this. It's a good light. Why? Because you can find a lot of problems from a good, thorough visual inspection. And whenever you see stuff that's melted, that's a problem, right? And that tells you that, hey, something there was affecting the current flow through the circuit, and wherever I have current flowing through a resistance, it's going to create heat and it's going to start melting stuff. So this could have simply been, this is where my problem was right here. I had a bad connection, and that caused the heat, and that caused it to melt down, so it just got worse and worse and worse. Or it could have been whatever is powered through that fuse, its resistance was too low. It was drawing too many amps. For whatever reason, the fuse didn't blow, and then it got too hot there and melted down. And to know the answer, you have to do some more measurements. But what you want to be is looking around with your light to find things like that, because a lot of your electrical problems are just, you can find those things by a good basic visual inspection. Now, I'll put this picture up with the battery one last time. Remember my formula, the KISS formula. Keep it simple, stupid. Don't overlook a bad battery, okay? Well, in the night on a story, and this happened right at the beginning of COVID, in the middle of our semester ended. I ended up where my pickup truck was at the house, and it sat there for a few weeks before I started it, because we weren't driving anywhere, right? So I go to start my truck and it won't start, and it's flooding out. And I know my truck has some questionable fuel injectors. They've been on my list of stuff to replace. Heck, I even bought the injectors and I just haven't got to putting them in yet. But I wanted to move it because it wasn't anywhere near my garage. It was over on the other side of my property, and it wouldn't start. And I figured, well, it's flooding out. I threw some spark plugs in there. First, I tried to clean the spark plugs, and I threw I did all kinds of messing around. And I was just at the point where I was like, well, crud, it keeps flooding out. I'm going to have to put the fuel injectors in it. I'm going to have to push it over to my garage, which is going to be a pain, and change these injectors. And just, you know, I knew I kept having to throw a battery charger on there. And I knew the battery was, you know, acting up. The battery was less than a year old. But I said, you know, let me test that battery. I tested the battery and actually had marginal test results. It was a quality O'Reilly's battery, of course, and wasn't testing out too good. So I exchanged that battery, took care of my starting issues. What was happening was that, yes, I have questionable injectors, and they're a little drippy, so they want to flood out the engine. But the computer on my truck, and my truck's 25 years old, but its computer, its PCM, it's actually programmed to try to compensate for things. So if your battery voltage starts to fail, if the voltage is dropping down, the computer saw that and goes, oh crap, the voltage is dropping down. Oh no, you know what, I'll compensate. And I'll turn on the injectors a little bit longer. I'll turn them on more to compensate for the battery voltage dropping. Well, between the computer turning on the injectors more and the injectors being just a little bit tired, a little bit drippy, that would cause the truck to flood out every time, and it wouldn't start. Through it now, probably if I had thrown the new injectors in there, that would have cured it. But by putting a battery in there where its voltage was not dropping as I was cranking it over with good volts, then it was able to crank it over quickly enough, and the voltage was high enough that the computer was happy with the voltage that it saw. It didn't add on time to the injectors. The engine didn't flood out. And guess what? I still haven't changed those fuel injectors, but it's on my list. So don't overlook simple things. Don't overlook a good visual inspection, and things as simple as a defective battery can cause all kinds of unnecessary headaches, okay? So good visual inspections, be on top of that. A lot of your electrical diagnostics you actually do with a flashlight, and just being very observant of things. All right, with that, do any of you folks have questions for tonight? And let me make sure I got the chat back up. I always get so many things on my screen that it's hard to see the chat box sometimes. Do you guys have questions for anything? Okay, well, don't forget that they're on Canvas. If I change my screen share here, I'm going to go back to, well, I guess I'll just, there we go. Screen share, there it is. Don't forget that in Canvas, if we go to discussions, there is always this tech help discussion. So if you have any questions, you can always hit me up on the tech help page, discussion tab, or you can email me. Now, Thomas has a question, and he says, what type of truck do you have? I have a 1996 Chevy. So I have an old Chevy, although it is OBD2 because it's a 96. So for me, that's still pretty new. So yeah, and cars will start doing that, compensating for voltage, battery voltage. I had a 88 Chevy Cavalier that did the same thing. It actually failed smog, and the guys at my shop, they had thrown all kinds of parts at it and all kinds of craziness. The car had a marginal battery, and I got tired of having to jump start it off the jump box. And so I ripped one of our new batteries that we would sell to our customers off the rack, and I just threw it in the car because I was frustrated. I didn't want to work on that car, and I was mad that the other guys couldn't figure out what was wrong. I threw a battery in it, and guess what? The car passed smog because the computer was no longer trying to compensate for an old battery. And that thing, I want to say it was like a 88 or maybe an 85. It was not very high tech of a car, but a lot of cars programmed into the computer will have that algorithm that they compensate for low battery voltage and do kind of funky things when the battery voltage starts to drop down. So yeah, my truck's a 96 Chevy, but I've seen that happen on lots of things. Tom here has a question. He has a 95 Chevy G20 van, and he can't figures out why the battery keeps dying. That could be a couple different things, right? It could be if the car's running, you park your van, and the next morning the battery is dead. That would indicate you that you have a parasitic draw. You have something leaching on the battery and sucking the battery dead while the car's off. That's called a parasitic draw. Think like a parasite sucking on you. However, if you jumpstart the van and you get it running and then you start driving it and then it dies out and the battery's dead, that would indicate that your charging system is not working correctly. Okay? And then every once in a while, I've seen batteries fail where they just won't, the battery itself will not hold the charge. But most common thing for this type of deal, if the battery keeps dying, especially when the car is shut off, is that you have a parasitic draw. And I'll tell you what, that will be a great, that's actually one of the things that we have planned to demonstrate in class, how to use your meter, even a cheapy meter like this one in my hand, to figure out that parasitic draw. Yeah, you could put a kill switch on there. You could disconnect the battery every time you park it, right? And that should keep it from dying if your problem is a parasitic draw. But you know, you shouldn't have to, right? If everything's right with the car, you shouldn't have to do that. And I'll teach you the way to figure out what that is. I'll tell you what, until I get to teach you that, why don't you do just what Mr. Cotton there recommended is disconnect that battery from now when you park it. At least it won't be dead when you start it back up again if it's dying when the vehicle's off. All right, everybody. Thank you for being with us tonight. I appreciate you being here. It's good to see your faces. I'm going to do this one more time. I'm going to stop my screen share. Stop share so I can get everybody back up on the screen. And I want to screenshot it one more time, just so I make sure absolutely that I got you. We got my attendance taken care of, and I'll give you guys points for doing that. But I really appreciate you guys being here with me tonight. I like your questions and input, both in person and on the chat. And I look forward to seeing you next week. Don't forget, check your announcements. If you've never heard about the discount programs, next Tuesday evening, we're going to have our tool guide to tell you about what those discount things are, a great way to build your toolbox. And then we'll have class on Thursday. We'll finish up this presentation that we're working on tonight, and then we'll get into some meter stuff. All right, everybody, you have a great evening. We'll see you next week. Okay?
Yeah.
Bye for now.
Bye.